Chemistry is the study of matter and how it behaves. We will be able to classify just about every piece of matter we find. So the question is, what is matter? Everything in this picture of the Manning Science Building, from the air up here in the atmosphere to the trees, to the railings, to the bricks, everything is matter. So what is matter? It's anything that has mass and takes up space. Takes up space means it has volume. I'm not sure I can think of something that has mass and doesn't have volume, but that's our working definition. In order to figure out what type of substance we have, one of the first questions we ask is, can we separate it physically? What does it mean to separate something physically? It means to filter something or decant something. Decanting is just pouring the liquid off of something before you filter it. Chromatography or distillation. Another thing that you can do is use a centrifuge to separate things as well. There are some different ways we can do this, and we'll take a look at that in the lab. One other thing you can do is use a magnet to separate things as well. So, the answer to the question of can it be separated physically determines whether or not we have a pure substance over here on the left. Pure substances cannot be physically separated, but mixtures can. We'll take a look at this pure substance side first. In order to figure out if it is an element or a compound, one of the things we can ask is whether or not it's made up of one type of atom. If it is, it's an element. If it has more than one type of atom, it's going to be a compound. Within the elements, we've already talked about this in class, but we can locate them on the periodic table based on whether or not we are talking about metals, metalloids, or nonmetals. And we had this stair-step line that separated the metals from the nonmetals. And the green ones along this border are going to be the metalloids. We know that even though aluminum is on the side of this stair-step line, it actually belongs to the metals. Some different properties here. We said that our metals are on the left, nonmetals are on the right. We just talked about these types of things being metals are hard and shiny, malleable, meaning we can hammer them into thin sheets, ductile, meaning they can be drawn into wires, they have higher densities. They are all solids except for mercury, good conductors of heat and electricity. They tend to react with oxygen and acids, and we noticed that they make a sound when we strike them. For nonmetals over here on the right side of the periodic table, instead of being hard, they are rather brittle. They're not shiny, they're dull, with the exception of diamond, which is just carbon, and iodine crystals are kind of, they are not dull. So these things are all going to be not malleable, not ductile, they have lower densities. Nonmetals can be solids or gases. Bromine is the only liquid. They're poor conductors, they do not make sounds. And one of the things to notice, though, too, is that 7 of these nonmetal elements are diatomic, which means we don't see hydrogen by itself. It is always going to be paired up with another hydrogen. And then the last part here is the properties of metalloids, and metalloids or semimetals can have properties of either one. They are usually shiny, brittle solids that look more like metals but act and have properties more of nonmetals. Another way to distinguish between elements and compounds is whether or not it can be chemically decomposed. Elements can't break down any further and still retain the properties of that substance. Okay, you can't make an atom break apart and still be an element. But with compounds, we can say, yes, they can be decomposed into the elements that make it up. So a compound can be either a covalent compound or an ionic compound, depending on what happens to its electrons. In a covalent compound, they are going to be shared between two different atoms, and in an ionic compound, they are going to be transferred from one to another. Some things to note, usually we have two nonmetals when we're making covalent compounds, like carbon dioxide, and this is where we say binary compounds that have just two different elements use these Greek prefixes, carbon dioxide, and these names end in IDE. If we have an ionic substance, we usually have a metal reacting with a nonmetal or a polyatomic ion, which we haven't talked about yet. But these bonds formed when electrons are transferred, and generally that electron goes from a cation to an anion. These binary compounds, again, made up of just two elements, those will also end in IDE, like sodium chloride. Ionic compounds are usually stronger than covalent ones, and so as a result, they have higher melting and boiling points than covalent compounds. Okay, back up to the top of the matter classification about whether or not it can be physically separated, and now we're going to go over to the right side where it can be, and we're going to talk about mixtures. In order to tell whether or not a mixture is homogeneous or heterogeneous, we are simply going to look at it and say, does it look the same throughout? Another way to say this is the composition variable? That means, does every piece of matter in there, every sample you take, will it be the same? So if it is, then it's going to be a homogeneous mixture. We also call those solutions. So anytime we're talking about a solution, it is a homogeneous mixture. If you take a sample of it and every time you get a slightly different composition, then we are talking about a heterogeneous mixture. You can see the different parts to it. A chocolate chip cookie or a muffin or a pizza or a salad, those would be heterogeneous mixtures. Within heterogeneous mixtures, just in terms of particle size, we can mention these things called colloids and suspensions. And basically, if we look from solutions to colloids to suspensions, the particles are getting bigger. And so as a result, those particles are going to settle out over time so that eventually they will be on the bottom of your sample. Another thing that's notable for mixtures is something called the Tyndall effect, and it has to do with whether or not light is scattered. So if you shine a light, whether it's a flashlight or your car headlights, through a solution or a liquid mixture here, if the light is scattered, like it is here and here, we say that this exhibits the Tyndall effect, and that is true for colloids and suspensions, but not for solutions. Another representation. Here are all of our different types of matter that we just talked about, and these are called particle diagrams, and we will work with these a lot this year. So we want to be able to represent pictorially or with a picture, with some shapes, what this matter looks like, whether we're talking about a chemical reaction or just a sample of, hydrogen molecules. So different ways to look at an element. Okay, remember that we can have individual atoms of an element over here, but we do have our diatomic elements. And so these are molecules, but they are not compounds. They are still elements. If we have a compound, then we are going to have two different types of particles, two different types of atoms that are connected there. And this would be a type of a covalent compound. And an ionic compound really looks like a regular repeating collection of these cations, the positive ions, and the anions, which are the negative ions. In a mixture, a homogeneous mixture is just going to look the same throughout, a uniform mixture. And heterogeneous, these are all different samples. Here's a mixture of atoms. How can you tell? Well, atoms are the smallest unit, so one little sphere is going to be an atom. And since they're two different colors, that's going to be a mixture of atoms since they're not bonded together. But here we have a mixture of an element and the compound, which is this particle there. And then here in this last one, we have a mixture of a diatomic element and a compound. So those are just different ways, and we will want to be able to represent and identify different pictures and what they are. Here's some real life examples, whether or not we are looking at silver and gold over here, or balloons filled with helium. Carbon comes in three forms: diamond, graphite, and charcoal. Those are all forms of carbon. Those are called allotropes when one element comes in different forms. Here is some liquid nitrogen. Here is some oxygen. Okay, those are in the air. The atmosphere is 78% nitrogen and about 20% oxygen. Compounds, we can have something as simple as water. Where would we be without water? Table salt, NaCl, sodium chloride. Sugar, table sugar. Sucrose, fructose, glucose, C6H12O6. Caffeine, here's a formula for it, and here's the molecular structure of it as well. So compounds, there are some examples there. Mixtures, one important thing to note, there is no one compound formula for it. Let me say that differently. No one formula. Okay. So here is the air, nice clear day, homogeneous mixture. Looks the same throughout. But if we had some clouds in there, here's air on a cloudy day. Now it does not look the same throughout because you have different components to it. Black coffee would be an example of a homogeneous mixture, but if you put some cream in there and swirled it around to make a latte, you'd have a heterogeneous mixture. If you went down to the Rapidan River, there'd be some water in there with some stones and mud and everything else, a heterogeneous mixture. And I do like tricks. Happy to see them in the dining hall. Would be a heterogeneous mixture, but in case you just eat plain yogurt, that would be a homogeneous mixture. One of the things we'll do this week in the lab is to start to separate these mixtures physically. So you'll have a sample and you'll have to break it apart into its components.